Hey there, it's Mo, bringing you another Machine Learning for Neuroimagers tutorial, Extensions Edition. For the purpose of this video, I'm assuming you've already watched the entirety of my machine learning tutorial. In this video, we will cover how to perform a principal component analysis, or PCA, on our morphemetry features and use them in our model. If you would like to learn more about PCAs, please visit my blog in the description below. Alrighty, let's get started. First, we're going to load in some libraries. I'm having some trouble getting ggbiplot installed on my PC due to some issues installing the DevTools library. This library will install fine if you're on a Mac or Linux operating system. Okay, let's read in our data using the read.csv command. And let's check for any empty cells in the spreadsheet which are coded as NAs and R while removing any that are there. For the purpose of this tutorial, we're going to remove the entire observation so it won't cause any troubles. Just like in the machine learning tutorial, it's important to scale and demean your data, which we can do using the preprocess command from the caret package. It's also possible to do this in the prcomp function too. I have them set to false because we've already done this with the preprocess function from the caret package. If you have ggbiplot installed correctly, this is what your plot should look like. It's a little overwhelming at first, but what it's plotting is PC1 on the x-axis against PC2 on the y-axis. All the dots are our observations and how much variance each PC explains of each participant. The jumbled words are our features and how much variance is explained by each PC for each feature. If the vectors are diagonal, like ours are, it means both PCs roughly explain equal amounts of variance in each feature. PCA produces many components, so how do you choose how many components to keep for your model? Scree plots can be used to determine how many PCs to keep. It's a little arbitrary, but a common method is using the elbow criterion. Basically, the elbow criterion is where the graph makes an elbow. Where you think the elbow is depends on what your criterion is for an elbow. The arrows indicate where component 5 and 10 is on the scree plot. For me, I chose 10 PCs to keep. You might think that the elbow is at 5 PCs, and that would be okay too. Now that we've selected the number of PCs to keep, we can add these onto our data frame. I'm also going to plot another biplot by adding a few extra lines of code to the last one we did to make it look a little nicer, by color coding our groups. Okay, let's take a pause and think about what we've done so far. We've pre-processed our data, performed a PCA on it, selected the number of PCs to keep, and have a rough sense of how our features map onto the PCs. In this case, the biplots didn't look very helpful to me. So let's explore some other ways. In the console window are the correlations between the features and the PCs, and in the main window are the loadings. The higher the R value, same thing as a loading, the more it contributes to the PC. Okay, now we have our PCs. Let's see how well it performs in our model when trying to predict sex. Here, we're setting up the cross-validation and then running the model. An ROC value of 0.873 is pretty good. As a side note, there's no exact ROC value to strive for, and it can be very dependent on the question you're trying to answer. Bigger is better as long as you're not overfitting, which is more important to take precautions against than trying to achieve a bigger ROC value. So that's good. Let's take a look at the lollipop graph. The lollipop graph is interesting and turns out how we would expect it to. PC1 being the most important for the model, and for the most part, the other PCs are in order. This won't always be the case in your model. Sometimes it will think PC3 is the most useful feature in predicting Y. It's important to pay attention to this graph because it can tell you a lot about how good your PCA is working or if you need to try something else. Let's check how it compares when we use all the features. An ROC of 0.859 is pretty similar, but the PCA still performs better. Now you can try playing around with how many PCs to keep and see if you can increase the ROC number. Of course, you risk the chance of overfitting by doing this, and would be very unacceptable to do in a publication. Thanks for watching, and until next time.